Every year, the global economy churns out roughly 400 million tons of plastic. A massive portion of that material escapes our recycling systems and drifts directly into the world's oceans, where it persists for centuries. At the exact same time, we are facing a global infrastructure crisis. Traditional roads crack, form potholes, and fail constantly. Repairing them requires endless, expensive layers of new asphalt, draining local budgets and taxing the environment. In April 2026, scientists launched a pilot project in Hawaii designed to solve both problems at once. Because of Hawaii's isolated geography, shipping trash off the island is incredibly expensive, making local disposal a constant challenge. To build their test road, researchers harvested 90 tons of raw ocean trash from nearby beaches, including massive, heavy bundles of discarded commercial fishing nets. The engineering proposition is clever. Take the oily, sticky black petroleum called bitumen that holds roads together and replace about 8 to 10% of it with melted waste plastic. We need to determine whether this technology removes pollution from the ecosystem or simply provides a convenient excuse to keep producing it. Making plastic roads work mechanically means forcing hard, solid waste to bond chemically with thick, boiling liquid tar. First, the scavenged plastics, specifically materials like polyethylene, found in grocery bags and milk jugs, are washed, dried, and shredded into millions of tiny flakes. This diagram compares the structural integrity of both materials under pressure. On the left, traditional asphalt snaps when hit with heavy downward force. But on the right, because the low melting point plastic flakes blend perfectly with the tar, the modified road can flex and rebound. That added elasticity is crucial when roads bake in the summer heat or freeze in the winter. Instead of splitting open and creating potholes, the plastic-infused surface easily expands and contracts. A university pilot project in Rockwell, Texas, put this to a real-world test. Their plastic-infused road stayed completely smooth and intact through weeks of weather exceeding 100 degrees Fahrenheit. The physical engineering successfully extends road life. However, laying tons of plastic directly into the environment requires a hard look at ecological risks. Environmental critics point to friction as the obvious threat. Thousands of cars driving over a plastic road could grind the surface into microplastics, tiny, invisible shards smaller than a grain of sand, that wash off the asphalt and poison the soil. To measure this threat, researchers analyzed stormwater runoff from the Hawaii pilot and simulated heavy traffic wear using a rigid laboratory friction test. Looking at this chart plotting the microplastic particle counts, the lab results are incredibly low. The polymer release from the modified pavement is almost undetectable, matching the baseline dust of a normal road. The overwhelming majority of microplastic pollution on any highway actually comes from the tires themselves. The rubber scraping off vehicle wheels dwarfs the road's footprint by orders of magnitude. There is, however, an unresolved end-of-life problem. These roads will age out in about 20 years, and right now, cities lack the specialized recycling infrastructure to safely extract and dispose of the plastic trapped inside them. While laboratory data dismisses the threat of immediate microplastic shedding, the lack of a long-term recycling plan remains a significant hurdle for future disposal. If we create a massive commercial market for plastic roads, do we accidentally give corporations a financial incentive to manufacture more plastic? Current infrastructure projects strictly utilize marine debris and post-consumer waste. Zero new plastic is manufactured to build these roads. There is also a secondary climate benefit at the factory level. Because the recycled plastic replaces up to 10% of the heavy, petroleum-based bitumen binder, building these roads directly reduces our demand for new oil. Assigning a tangible economic value to ocean waste creates a powerful local incentive. It makes it suddenly profitable for communities to fund and organize massive beach cleanups to harvest materials. These roads effectively function as a massive quarantine system, locking away millions of tons of waste that already exists in the environment. Finding a reliable place to bury our old garbage does not solve the source of the problem. Society must maintain aggressive efforts to phase out single-use plastics entirely. Turning ocean trash into infrastructure is a brilliantly pragmatic bridge to fix our past mistakes, as long as we never treat it as permission to pollute our future.